Hello, teacher. Hello, students. Welcome to today's lesson on the elastic behaviors of matter. We are beginning a new unit today on the properties of bulk matter. In this unit, we are going to learn about malleability, fluid statics and dynamics, and heat and temperature. Today's lesson will focus on elastic limits, the different types of stresses, and the formula for expressing stress. I am excited to be starting a new unit with you. Let us begin. We have already learnt about the interaction of forces with bodies. A single force causes a body to change speed. Two equal and opposing forces cause a body to deform. There are four main kinds of deformation. They are called tensile deformation, torsional deformation, shear deformation, and compressional deformation. Tensile deformation is a result of pulling forces. Torsional and shear deformation are the result of twisting forces. Compressional deformation is the result of pushing forces. These types of deformation all fall into one of two categories. They may be elastic or they may be plastic. An elastic deformation is essentially temporary. When the force that is causing the deformation is removed, the body returns to its original shape. Think of balling up a wetted sponge in your hand and how it springs back to its usual shape as soon as you stop squeezing it. You are deforming the sponge in an elastic fashion. Plastic deformations are more permanent. Irreversible changes happened in the body when it was deformed. In a metal, layers of atoms may have slipped over one another. The body will not return to its previous shape after the forces have been removed. If you crumple up a soda can, the can will not return to its original shape when you put it down. The can has been deformed in a plastic fashion. All materials have an elastic limit. There is a certain amount of force that will cause them to stay permanently deformed, but that amount can vary widely between types of materials. Steel, for example, has a low elastic limit, so tends to stay in whatever shape it is pressured into. Rubber, on the other hand, has a high elastic limit, so tends to spring back into shape as soon as the pressure is removed. It is time for an activity, students. Please form groups and list 6 materials. 2 of them must have a low elastic limit. 2 of them must have a high elastic limit. For the last 2, please name 2 materials that have a moderate elastic limit. Think of materials that stretch, but can still return somewhat to their original shape. Please get started.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I wonder what materials you were able to name. For materials with a low elastic limit, you might have said concrete, or carbon fiber, or even diamond. Materials with very high elastic limits include rubber, as we have said, but also cork and some plastics. It is ironic that plastic should exhibit such elastic behavior. Materials with moderate elastic limits were probably more challenging to think of. Some of these include wool, grass, and spider webs. Good work. It takes more force to deform a body that has a low elastic limit. Let us take an example of a copper wire. If we wish to measure the specific amount of force needed to extend it, it is not enough to simply state how much force we are applying. The amount of force you could apply to stretch a thin copper wire might be useless when used on a very thick copper wire. To compare like with like, we must measure the tensile stress being applied. This is defined to be the tensile force, called F, divided by the area of cross-section of the wire. The tensile stress is expressed in newtons per square meter. If we wish to measure how much the wire was deformed as a result, we must do more than measure how much longer the wire has become. The ratio of the wire's change in length to the wire's original length demonstrates its tensile strain. It is necessary to measure the deformation by the tensile strain, which is the extension called delta L divided by the wire's original length, L. It is time to put this new knowledge into action, students. These are the physical properties of two wires, along with their extensions and the force it took to stretch them. I would like you to calculate the tensile strain and stress for each. Please start now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Let us look at the solutions to this problem together. Remember that the stress is calculated by dividing the force by the area. For wire A, that would be 4.9 divided by 2 times 10 exponent negative 3. In other words, the stress on wire A is 2,450 newtons per square meter. For wire B, we make a similar calculation. 10 divided by 3.5 times 10 exponent negative 3. That comes out to about 2,857 newtons per square meter. The tensile strain on wire A is found by dividing the extension by the wire's original length, which is 0.05 divided by 2. The strain on wire A is 0.025. Following the same steps, we discover that the strain on wire B is 0.09 divided by 3, or 0.03. Well done, students. That brings us to the end of today's lesson. We have learned about elasticity, plasticity, and tensile stress and strain. Keep working as hard as you are, students, but please don't strain yourselves. Until next time, thank you, teacher. Thank you, students.